Welcome to Complexity Made Simple, and the story of today's tutorial is the measurement system analysis. Now, just before we get on to SPC XL and we take a look at how the software deals with measurement system analysis, I just want to talk about what we use MSA for and how we set the test up, and then we'll go and take a look at how the software analyzes the data. So a key point to think about is that every measurement system you have essentially is wrong. You have measurement error in every measurement system, and the measurement error always increases the variability of the results. So what's going on is you have a manufacturing process which is producing a distribution. This is what's coming off the machine. You would like to see that, but unfortunately, before you can see that, you have to put it through another process. This time, you have to measure it. And what you actually see is those two added together. So what you end up with is something more variable than what's really there. So you've got the underlying distribution, you've got this little bit of inflation here, and this inflation is caused by the error in your measuring systems. And what an MSA is basically going to do, tell you how big that is effectively. And of course sometimes it can be really awful. So you can have something where the machine is producing something brilliant, you're seeing something that looks terrible. If you put specs on the thing, you're seeing defects. It's making it look like you've got a defect rate when really you haven't. Of course, where are you trying to fix the problem? You're out on the machine trying to fix the problem. The problem isn't with the machine, the problem is with the measurement system. So you can work on this thing all you like, don't fix it, because the maximum amount of error isn't being created by the manufacturing process, it's being created by the measurement system. So what MSA does is it tries to quantify that error for you and then tells you whether you need to fix the measurement system before you try and do anything else, because if you can't measure it, there isn't much point trying to manufacture it, really. So it's telling you if you've got a problem with your measurement system or not. Okay, so that's what it's for. Let me just get rid of that those notes a second. So let's just talk about the process, the procedure for doing this. The basic procedure is this. Now, first of all, the main thing to think about is we are dealing with, this is for variable data. So this is measuring stuff. So we are talking things like coordinate measuring machines, micrometers, jigs maybe for measuring millimeters. You could have jigs for measuring volts, jigs for measuring decibels, all kinds of different scales and output measurements that you're trying to measure, but it will be variable data, something on a scale. We're not dealing with pass and fail here. Okay, so I know sometimes you've taken the measurements, you're measuring the volts, then you get a red light and a green light off the jig. That's pass fail in nature, but the jig itself had to measure on a scale in order to make that judgment. So providing you can see the number, you can still do this type of MSA on that type of jig. So it's variable data that we're looking at in this tutorial. What are we going to do? First thing we're going to do, we are going to select 10 pieces at random. Most important that that's the case. They must be at random. They must represent the inherent variability that the measurement system is going to see. So what you don't want to do is pre-select. You don't want to say, well, I'll give you 10 good ones or I'll give you 10 bad ones. That's not the point. The measurement system is supposed to be able to see the difference between good ones and bad ones. So what we want is just 10 randomly selected out of the process that the measurement system would normally see. We are then going to give those parts to the same measurement system twice. Okay, so you're going to give it to the same measurement system twice. And effectively, Each measurement system will measure the part 2 times each. Now it's important, because that's going to be the case, it's important that they don't know which piece is which, and when they repeat the measurement, they must not know which piece they have in their hands. So if you number them, so if you number the parts 1 to 10, do it blind, so that the measurement system, especially obviously when this is a person, they will be conscious of this fact. When it's a machine, the machine is never going to know when you repeat the measurement that it's number 3 that it's looking at again. But if this has people involved, this is important. The people must be blind to the part that they're being given. Obviously, if you measured a part and you said, well, this part was 15.38 millimeters, if I ask you to measure it again, you'll fiddle about with the measurement system until it says 15.38 again. And you'll say, there you go, I told you it was 15.38 last time, it's 15.38 this time. That is known as bias. We want to remove bias, and therefore they must not know which piece they have in their hands. And the best way to do it is to give them the 10 pieces in order, 1 to 10, then give them the pieces randomly in a different order the second time, and then they won't remember what they got. So each measurement system is going to measure it twice, and then you're going to measure it maybe 2, 3, 4 times. Each measurement system is going to have a go at this. So each system measures twice each. Okay, so, and that's the setup. That's the way we create the data for measurement system analysis. Okay, now I've got a set of data where we have 2 measurement systems, each measuring the parts twice. 10 pieces have been taken at random. We're going to take a look at that now, and we're going to see how SPC XL does measurement system analysis. So let's just flick to the Excel. Oops, wrong one. That's the one. I have the data there, so let's just populate the data. I'll just color it in yellow so you can see the actual measurements. So here are the measurements. We were measuring the diameter of the head of a nail. Whoops. Let's come out of there. We were measuring the diameter of the head of a nail. Okay, so so here's the data. Look, you can see the data is in the yellow fields. That's the measurements that were done. We've taken 10 nails. So these are just roofing nails, just something for us to measure effectively. And we are measuring the diameter of the head of the nail. And we've used a micrometer or a vernier caliper to do this. So very simple measuring equipment in this case. So there's the data set in the yellow fields. We've also worked out the average, and we've worked out the range, but it's the yellow data that we're really interested in. So let me set up a table for that data to go into, because unlike some of the other tools in SPC XL, MSA wants the data to come in a template. So look, MSA gauge capability, create a template. All right, says how many operators did you have? How many measurement systems did you have? How many replicates, repeats did they do? 2. And how many parts did you give them? 10. And optional is the spec. Now I'm going to put a spec of an upper spec of 6.5 millimeters, a lower spec of 5.5 millimeters. So we have a whole millimeter here to go at, and the piece of equipment that we're using to measure the diameter in this case is measuring to hundredths of a millimeter. So we should be able to do this pretty well, shouldn't we? Hopefully. You'll see now whether we do it pretty well or not. So if I click OK to the template, it just creates an empty zone, look, for operator 1, operator 2. So I'm going to go pick up the data now, and I'm just going to copy and paste it in. So yellow fields, that's all I'm taking, don't need the rest. So just take it, paste it straight in there, operator 2, take it, paste it straight in there. So we've got the data. Now, just a simple thing for you to do, by the way, before you go any further with this, just use your common sense. Forget the maths for a second. Look at this. This row here. That's 4 measurements of the same item. They should all be the same. And look at them. The lowest is 6.03 millimeters. The highest is 6.27. Almost a quarter of the tolerance has gone just by measurement error. That's not great, is it? That's giving you a sense of how good this system is, even before you ask the mathematics to do some calcs. Okay, so use your common sense. You know, don't just go mathematics. The same thing is true here. Look at this one, 611 place 641, 0.3 of a millimeter difference for the same piece. Yeah, so how's that possible? Yeah, you can see error even before you ask the mathematics to intervene and quantify it for you. So let's ask the mathematics to do some work for us. So back to MSA gauge capability, and the version we're going to use is ANOVA analysis. You can use X bar R analysis. It is trying to do the same calc. ANOVA is a better estimate of error, so I'm told by the mathematical experts. So we are going to use ANOVA analysis. Right, so let's click on that. Okay, now then, what we get is a table of data, and then we get a graph, a graph, a graph, 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 a graph. Okay, so lots of graphs, lots of information. Now I'm going to show you how I do this. Okay, so I'll show you how I do it, and I'll show you what graphs I use. I don't use all the graphs. I only use the first graph and the last graph, and I use the table, the summary statistics that you saw at the beginning. So I'm going to use this thing here. All right. So just before we go on to that, let me just say something about MSA that's kind of useful. So we'll just go back to that page. So if I say we want to answer 3 questions with the MSA, and the first question is my system any good? Okay, is my system any good? Now, assuming the answer to that question is no, we have other questions to answer. But if the answer to that first question is yes, your system is perfectly adequate for what you're trying to do, there are no other questions to answer. But if the system is poor, is my system any good? No, it's poor. The next question is, where is my problem? And the third question, what am I going to do now? Yeah, so they're the 3 questions. Is my measurement system any good? Where's my problem? What am I going to do about it? All right, so they're the 3 questions that we are about to answer, and I'm going to show you how to do that with just with 3 of the pages that have just been created. So let's go back, and I'll show you which pages we are going to look at. So the first question is my measurement system any good? And we are going to answer that question by these 2 values here, precision to tolerance and precision to total. Now those 2 numbers should be 0.1 or less. Now you can see they're a hell of a lot higher than 0.1. Therefore the answer to the question, is my measurement system any good in this case, is no. Okay, so let's just talk about what precision to tolerance is. Precision to tolerance. The way to look at that 0.56 is to think about it as a percentage. 56% of the tolerance is being consumed by measurement error alone. 56% of my tolerance is getting used up by measurement error. So the process has only got 44% left to get into. All right. By the way, these numbers don't look great. Don't think you won't see this with your measurement systems. I see these numbers a lot. You know, certainly in the 40s and 50s, quite a bit. So the next one is precision to total. And what that's saying is, of all the variability I'm seeing, how much of it is measurement error? And again, the way to look at this, in this case, 32.8% of all the variability that I can see, 32.8% of it is measurement error. So in other words, the distribution is being made 30% bigger by measurement error. Now, of course, if this comes into contact with tolerances, it's going to make my reject rate look much bigger than it really is. And that's one of the problems with measurement system error. It inflates your defect rate. Okay, so first question, is my measurement system any good? No. Where's my problem? Now, I'm going to answer that question partly by these values. Let's put them in a different color. Let's put them in the orange fields. Okay, now then, the standard deviation that's coming from reproducibility and repeatability. The English language is fantastic, and it comes up with these words sometimes. They're quite difficult to understand. Let's talk about what repeatability is. Repeatability is within system error. In other words, how well does each operator repeat their own result? Okay, that's what repeatability is. Reproducibility is between system error. So in other words, do the two systems agree with one another? So it's within and between repeatability and reproducibility. An alternative name for this technique, by the way, is gauge R&R, and the gauge R&R stands for repeatability and reproducibility. Now, all I'm interested in these two numbers is their relative size to one another. It doesn't really matter what the number is, but I just want to know, where's the biggest problem? Is it within or between, or are they both at a similar type of level? And that'll help to tell me what to do next. Now, in this case, the within system error is much bigger than the between system error. It's twice the size. So my problem primarily is within system, but there's also some between system error as well. But we're going to look at the within system first. So there's sort of 1.5 questions answered. Let's go and look at the graphs now and answer the final parts. So the first graph here is a plot of the averages. All right, so the average size that operator 1 saw for nail 1. So if we look down here, here's nail 1. Here's the average for operator 2. Here's the average for operator 1. Do they agree with one another? Not quite. There's a little bit of between system error. Well, we know that because we saw that in the numbers. However, a nice thing about this diagram is that the lines move in the same direction. So when operator 1 thinks the nail got bigger, operator 2 agrees, and vice versa. And that's a nice thing. You know, there is error between them. We'd like to make those closer if at all possible. But if you saw them not agreeing with one another in the pattern, that would be quite a worrying sign. In other words, operator 1 thinks the nail got smaller, while operator 2 thinks the nail got bigger. Yeah, that wouldn't be a great pattern to see. But this is, we're not going to use this graph because too much, because the error is not between system, the error is within system. So the last graph that I use is the very last one. So if I scroll to the end, there is a range chart. Now what this diagram is showing me is the difference for operator 1 and operator 2 between their two results. So a great result to see on this graph is everything at the bottom. 0 would be the best result. So here there's only one look that was 0. What that means is that on nail number 8, operator 1 agreed with itself. Let's look at that for a second. Let's just go to the template. Nail number 8. Look, operator 1 got 592 against 592. There was no difference between their two measurements. That's the perfect result. That's what you want to see. Because that's not what we are seeing now. And the range chart is showing you the ability of each operator to repeat its own measurement. Remember, repeatability was our problem. So look, operator 2 is clearly really poor at this. It cannot repeat its own measurements twice running. So okay, is my measurement system any good? No. Where's my problem? It is within system. Primarily, it is within operator 2. What are we going to do about it? Well, we're not going to sack operator 2 now. That's the nuclear option. What we're going to do is we're going to ask operator 1 what they do. And then we're going to create a good standard operating procedure based on operator 1's knowledge. We'll write it down, train it out, and we'll see what happens. See if the process gets better. It's possible, the reason why we're going to interview operator 1, it's possible that operator 1 has a little set of experience or a little set of rules in their head, and you can't see them using this experience, but if you wrote it down, you could teach it to everyone. So a little example is if the item happens to be oval, and in this case these nails are oval. If the item is oval, then operator 1 might say, well, I've noticed that the parts aren't round. So what I always do is I twist it around until I get the biggest size, or I twist it around until I get the smallest size. And that might give this operator the skill to get much closer to its original result. Operator 2 might have not been relatively new, might not have noticed that problem yet, and therefore doesn't do that, doesn't use that little trick. And if you watch the two operators, you probably wouldn't even notice that operator 1 is doing something slightly different to operator 2. So go and interview the guy, see what he says, right? And then write it down. Fairly straightforward. Okay, so is my measurement system any good? Where's the problem? What am I going to do about it? Now that's essentially it. There's MSA done, all right? But let me show you the graphs that I didn't use, all right? So there's some graphs I didn't use, and let me show you why I don't use them. The first graph is this one, which is trying to show you how much measurement error is inflating the distribution. Now this never looks right. I don't know whether it is right, but if you look at that, we said that that distribution is being inflated by 30%, I think. And it just doesn't look like that, does it? So that diagram, I'm not sure if it works properly, but I never find it useful. So I just use the three graphs that I've just shown you. Now the next one, the misclassification rate. Now the misclassification rate graph is essentially quite useful. It's additional information. It doesn't help you necessarily solve the MSA. What it does do, however, is it helps to maybe give you a little bit of impetus to put the problem right. So let me just blow up the numbers in the top left-hand corner. It's got 20 nice and large. There we go. The misclassification rate. 453,000 potentially are misclassified. What that's saying to you is that you could be misclassifying up to 45% of the goods using this measurement system. Now the way the diagram works is that the blue distribution is the results that you saw. The two red lines here in the middle, oops, the two red lines, well, I'll do that in a second. The two red lines, they're the specs, and the zone where the blue and the red distribution, the red distribution, by the way, is the measurement error. Where the blue and the red distribution intersect is the danger zone. because what could happen is you could have a part just inside tolerance, but measurement error picks it up and makes it look like a defect. You could get the opposite problem. You could get a defect sitting out here. Measurement error picks it up and makes it look like a good one. So you could be sending good parts to the bin. You could be sending bad parts to the customer. You know, have you ever had the customer send you a part and say, "This is rubbish, why did you send me this?" You ever wondered how that escape happened? Well, part of it will definitely be because of measurement error and the misclassification rate. Now, the misclassification rate in this case is very bad, so we would want to sort this out pretty quickly. So the misclassification rate is extra information, but it doesn't help you answer the problem. Is my measurement system any good? Where's my problem? What am I going to do about it? But it does say you better get on with this. The next one. Now the next one is a Pareto of where all the variability is coming from. Is it repeatability, which we knew that it was? Is it reproducibility? Is it part to part? Now we've already taken good order of this knowledge by looking at the standard deviation number over on the data table. So the orange data is essentially what we looked at. Let me just find it. We've already looked at it here. So I don't use this diagram again. It's not adding anything to what I've already decided. The X bar chart is the two averages sitting side by side now. So we've already looked at this data, but we saw it on a better diagram. It's the same data as this, but this diagram where they sit over the top of one another is much more useful than this one where they sit side by side. So again, I don't use that one. I use the table of data. There it is. I use the yellow field numbers to tell me, is my measurement system any good? I use the orange field numbers to help to tell me where is my problem. And then I use the first graph, and I use the last graph to make my decisions. Is my measurement system any good? Where's my problem? What am I going to do about it? And that is MSA using SPC XL.